So it's a pleasure and privilege to introduce our first speaker, Mark Petrotta, who's been almost a personal hero of mine and for many other systems engineers and software engineers. And he's been a long time advocate of the system as code paradigm and that systems engineering should go beyond diagrams and should be executable, connective, robotic operating system frameworks, and really be a part of the software engineering, essentially paradigm where everyone is living in this, system as code paradigm. So it's a pleasure and privilege to introduce Mark, who is a principal engineer at SSI, one of the leading systems engineering organizations in the US. So without further ado, welcome, Mark.
Thank you so much. That was a wonderful introduction. Can you hear me okay? Just as an audio check. Am I coming through in the room?
Here, okay, yeah.
Okay, perfect. And hopefully you can see my slides as well. Well, wonderful. Yes, it's an honor to be here, and it's actually an honor to present this topic, which is, believe it or not, a little bit of a personal journey for me, which seems funny to say, but as I was developing this presentation, my original title was the convergence we've been waiting for. What software scale brings to systems. And I realized that was far too passive. It really is this convergence to the way that software is scaled. It's not waiting. We've really been asking for this. This is really a capability that I think is going to dramatically scale systems engineering. So with that, hopefully this comes across okay. There we go. Okay. Like I suspect many of you, I come from a software engineering background. I started in about 1995, and I realized that over the course of 30 years, I guess that makes it, I've gone from thinking myself as a software engineer to a systems engineer, although I've gone back and forth a few times in that. It's truthfully not a straight line, but it's useful to think about that. I started as a software developer, with using a software developer for space-based systems, really using UML from an early stage for a lot of the systems that we didn't have access to. So to improve integration, the ultimate state, using UML in its earlier forms. And then moved into doing software-centric systems engineering and really using what I call proto-SysML, early versions of UML that were tailored for the formal release of SysML to do a large-scale ground vehicle system. And in fact, that's really been my system engineering career, started in doing ground-based and robotic systems. And it really, working on a large-scale program, it's around 2007, I realized that distributed and scaled system engineering was actually, I won't call it a pipe dream, but it really was much more difficult than we'd anticipated. And we thought that this would lead to convergent system engineering, but there really were still, when you had companies around the world collectively working on the product, it was still very, very challenging. And more recently, last really 15 years, I've been focused on systems architecture, but with an interesting computational systems engineering. How do we move from, as was said in the introduction, how do we move from diagram focused system engineering, which, as we teach systems engineering, in fact, I'm an instructor for University of Michigan and Georgia Tech, teach the system engineering and MBSC courses. As much as we say the diagrams are not the model, it still is a very effective way of teaching systems engineering is to use the model, use the diagrams. And so I've been very interested in computational systems engineering, how we can use computational resources to improve our systems engineering effort and exploration, design exploration. And that really led to another question. And over the last, this century, software, coming from a software background, just the scale of software engineering has been phenomenal in terms of the complexity of the software and the ability for multiple people to simultaneously work on a software development effort. And it made me wonder this question: is internet scale system engineering even possible? And that has focused my experience working in digital engineering with, again, crossing that line over to augmented systems engineering, which is really my preferred term for AI for SE, but really how do we augment the SE effort using the just phenomenal growth in AI resources. So this has been a bit of my personal journey going from considering myself a software engineer to considering myself a systems engineer, while always really going back and forth. And so this really made me think about the history of software and how it's changed since the 90s, when, at least when I started. And I've focused on the history of software over this time period in 2015. I think quite a bit's done more recently with containerization kinds of things, but I think these are the most useful features when it comes to scalability of systems engineering. There was the transition from waterfall approach to agile. And from personal experience, I can think of times working on large scale software projects where the first time I met the client was when, or the end user was when we were actually deploying the software. And just what a radical shift it is to agile to get much tighter feedback into the functionality of the software. Software was geared for really limited reuse in the 90s. Everything was developed in-house, and there was a tremendous move towards both open source and reuse. That's really changed the perspective from having to maintain the full code base to really what's the differentiator of that code base. What's new and unique to the product we're developing. A move from manual testing to automated testing and continuous integration. That really was, in the 90s, testing was sitting down with an inspector. I was working in aerospace, space-based, and so I actually had someone sit with me and run through the test cases. And as a joke, we would often buy garlic bagels that morning to try to speed up the process of getting approved for release. So very, very manual. Monolithic architectures and a movement towards modular architectures and microservices. It really was one big drop versus modular architectures or components where you can now have teams simultaneously building pieces of the software architecture. Limited scale of collaboration to really effectively scaled collaboration. And I'm looking right at Git when I say that. If anyone remembers CVS or even Subversion, some of the tools that predated Git, it really was scaled towards a centralized architecture versus a distributed architecture. And finally, a siloed culture versus a DevOps culture, where you have a view of the whole pathway when you're developing versus really just a focus on the software development effort itself. So number of technical enablers that came along the way that were there, that developed because of the need for scalability of software. Git, of course, Maven, as was mentioned, NPM, for these different kinds of package managers, GitHub just in terms of the ecosystem for open source, and so on. And Jira, of course, for problem reports and ticketing. And it made me think, what were really the key takeaways from software scalability as it scaled tremendously? And these were my top 7. Yours may vary, but these were my top 7. Humans don't scale, but procedures do. You can put together a process, you can put together procedures, or you can put together guidelines, but really when it comes down to it, they just aren't reliable control surfaces as you grow. Whereas executable procedures are scalable. Pipelines turn promises into properties. Really, instead of relying on people to remember best practices, those 20 steps that are required, we encode those all as code. So they really give us a repeatable output. Feedback moves left. When you can do automated checks, automated testing after every change or even after every commit, depending on how you work, it really compresses the error half-life. You find errors, detect errors much faster than you did than relying on a final test or inspection. Consistency beats heroics. Reproducible build, deterministic tests, all these kinds of things give us fewer surprises and faster recovery. Interestingly, speed comes from safety. This is something that was not always obvious to me at the start, but when you had the safety of ability to roll back, to change, understand where a problem came from, you progressive delivery. All these things meant that we had a fallback position, so we could operate faster, knowing that we could always understand if a problem was introduced, where it came from, what feature branch it came from, and so on. Governance is code. We could put policy in the pipeline. And so as much as I appreciate model guidelines, I've certainly helped develop model guidelines as approaches, but governance actually could be introduced as code and could be run uniformly. The tests, we know when we have a commit, we know that all of the tests have been run, compliance checks, linters, and so on are part of the pipeline. And finally, platforms amplify the effect. And by that, I mean that once you have a pipeline, you can repeat the pipeline, sort of the golden path, as they might say in software. Once you have something that works for you, you now have a repeatable platform that will give you consistency from program to program. In fact, this is one of the key challenges of aerospace, where every program feels like a bit like a startup effort. Now, this, knowing that from software, this happened to put together as part of my work at SSI. Did a survey, this was I think back in 2019, where we said, really for systems engineering, what would it take to scale systems engineering? What are our challenges? For instance, a very centralized architecture, very tool focused, and we want to move towards a decentralized architecture and model focus. We want to look at model reuse versus this mentality of create, store, and discard. As I mentioned, your experience may differ, but for me in aerospace, a lot of times programs tend to be like startups. In fact, I started my career at startup companies in the dot-com era, and a lot of ways, every program felt to me like being back in 1995, where everything was created new and all processes and procedures were created new, versus a mentality of reuse. And of course, many more, we see degraded performance at scale. We've observed that in SE efforts, and we want improved performance at scale. So this happened to dovetail with questions about what would actually enable the scalability of systems engineering. And this is where I first started interacting with Systemetry. So I started asking myself for SysML v2, which felt like the light at the end of the tunnel for many of us who are looking for scalability of systems engineering. Really, what is involved with V2? What does it give us, and what are some of the challenges? And this, I went to in Cozy. This was the IW, I think a year or two ago, where I saw a demo of some of the early V2 tools. And I realized that there was actually two paths, and one of them was a text first. Some people call it version control textual notation, VCTN. I like that acronym. You could also call it as text authoritative versus model authoritative. And what I came to realize was, if you work using the textual notation, you really have this decision point where you're either going to stay on the top line, where you're going to stay authoritative in the source code, or you're going to import it into the model and then keep working in the model. So kind of an import and done. And I was in this room, I think this was out in LA, and I realized 30% of the people absolutely wanted to stay in Git, stay in code. Really, they were saying stay in Git. 70% wanted to import and be done with it. And I realized there was really a split, or a bifurcation in the way people wanted to work, and it made me think there was actually two development paths. One where we're going to use software scalability, and I would say Git, Jira, so problem reports and feature branches, where the text stay authoritative, and the other where maybe the text is used, maybe not. You could stay still diagram focused or model focused. And in fact, the V2 service as an API is very model focused, and so you can of course use the textual notation to build a model, but ultimately it stays very model focused or model authoritative. So two very different paths, and I really am focused on the top path. But it was important for me to understand where people were coming from, and really about 70%, I'd say, actually hated the idea of staying in code or being authoritative in Git. Very, very different pathways. Okay, so that led me to an experiment. Can I do VCTN or text authoritative using stock open source DevOps tooling. And trust, this was before I knew anything about Systemetry or Seaside or the great tools they've done. So full deference to the hosts of our conference. This was something I just did. Actually put this in GitHub as my experiment. But can we do VCTN using open source tooling? I personally developed a build system, just a tailored pilot implementation. So I use Gradle. I like Gradle. With a Maven-like asset locator, I was really interested in dependency, how we handle dependencies in system engineering models, and of course, build automation using Jenkins, a popular build automation tool. So now, what would I learn by doing this? And generally speaking, the stock software tools and methods will suffice for most of the way. What I had to build was just the build system itself. In other words, going from the textual notation to the model, really just a wrapper, so I could use Gradle. And then a component locator. I happened to pick something like Maven-like component location. I wanted to be able to point to my dependencies and use a tool like Nexus for a component management. Main point of this, stock tools worked excellently, just really beautifully. And if you are used to doing command line work in using software methods. Okay, so that said, it's definitely possible, and
Mark,
no major. Yes.
The talks are just 15 minutes, so if you could, try to summarize and wrap up so that we can give the chance of the speakers to speak, that would be great. So,
Yep. Sorry about that. Time management is not one of my skills. I try. Okay. So that really led to me, and this is my conclusion. So 4 major things that I'm looking forward to. Everything is code Git native work. And by that, I mean problem reports, feature branches, everything that Git is really good at gives us that massive parallelism, reproducible history, and so on. Component libraries, like I mentioned, I'll put a plug for OMG. I'm part of the RAS 3.0 effort to have more standardized reuse methods of reuse. Automation end-to-end, CI/CD, that gives us that policy in the pipeline, so to speak. And finally, one more that wasn't obvious to me until I got into digital engineering, but observability of the digital engineering system. Software uses this term DORA, DevOps Research and Assessment. There's other kinds of metrics that are in use, but you can't scale what you can't see and improve. So understanding, the rate of change in your pipeline, where problems are being introduced, and those kinds of things. So really metrics in your pipeline. Those are my 4 changes. So my conclusion, for systems as code, this conference, when systems feel like software, scale follows. Ship smaller, automate more, and measure everything. So that's that. Of course, I'm sorry about apologize for running over. I do actually try to respect the time slot. 15 minutes is just so short. So
thanks so much.
Thank you for having me.
It's really a pleasure.